In the Ignite program, we're focusing on semiconductor quantum technology, and we're making use of quantum dots to define qubits. Here we'll focus on quantum dots, how can we make quantum dots, and how do we operate quantum dots. The idea of using quantum dots for quantum computation is now 25 years ago. So in the seminal work of Daniel Loss and David DiVincenzo, they proposed to use quantum dots for quantum computation. And here you see the first figure of their paper. And I believe it's a very strong, very important figure. And so I encourage you to explore really the details of it. First of all, you see that these circles, these quantum dots, are not perfectly circular. That was actually intentional. Why? Because they would argue that each and every quantum dot is different. And in particular, if you're going to define a qubit on it, it's very important to understand that every qubit will have a slightly different personality. And so a key question is, what do we do with this personality? Can we make it, improve it? Can we make systems such that there's no such a personality? Or maybe we can live with it. This is one of the essential questions in our community. The second part is, you see this arrow here, denoting the spin that we're using as our qubit. And you see that there are different quantum dots. One is a FM, a ferromagnet. The other is an electron. And you see that these axes are slightly different. This may denote that these spins may be in different states in different quantum dots. But maybe it may also relate to different kind of questions. What is, for example, the spin quantization axis in these quantum dots? And so it's good to strongly focus and study this paper, as it's still one of the key papers for community today. Now, having this qubit personality in mind, that every quantum dot is slightly different, now envision something like this. We want to build a quantum computer with millions of quantum dots. So how are we going to build a system such that we have, for example, a single electron underneath each and every gate in a scalable way? This, of course, seems to be like almost contradictory to each other. And I want to show you that, well, there's maybe room for thinking that after 25 years, these qubit personalities are slowly fading away. Let's first see the development on the materials. Of course, the better the material, the better the devices later on. The better the fabrication, the more uniform we can define our system in. In the last few years, we've seen a strong push on strained germanium. So in 2018, we were just growing the material, making the first quantum dot. And then we see every year a slight improvement in the device, going from a single quantum dot to a double quantum dot, from a single qubit to a 2-qubit system, controlling 4 quantum dots, controlling 4 qubits. And today, we can already control 16 quantum dots in a 4x4 array. Of course, very far away from the millions of qubits that will be needed for a future fault-tolerant quantum computer. But it shows that in a matter of years, we could really scale to larger systems. Now, in this 4x4 array, we show that we can have an odd number of holes and a few number of holes in each and every quantum dot. At the same time, it's clear that if we don't improve the way of working or these devices, this will not allow to scale definitely further. How do we get there? Let's first zoom in on this experiment where you see here the transition lines. And using a semi-automated machine learning technique, we can identify the charge transitions and then tune and navigate to a space where you either have 1 or 3 holes in the entire array. But of course, one would argue, okay, if we have a larger device, we want everything to have a single hole or everything 3 holes. At least you want everything to be identical. So is this possible? Or how can we otherwise live with it? This is a key question. And these are these qubit personalities. So let's maybe compare to a stability diagram that I actually measured myself in Australia a few years back. I was super excited by this. This was the first time that we control 2 quantum dots, 2 qubits. If I look back at it and you see the position where I have 1 electron in each of the quantum dots, then the gate voltage required to get to that point is quite different for each and every gate. Right? So this is clearly not a very uniform system. Also, the time to control it is, it takes a long time. For example, back then it took me several months to get to this point where, and also control qubit operation. Today, the 4x4 was tuned significantly faster than that. But still, we don't have really the uniformity of what's needed here. So on the right, you see an image, what we can do today. Here you see these dashed red lines, and you can see that for both the gates, plunger 3, plunger 4, at 1 volt, we can tune to a point where we have 1 electron in the system. So we can go to the 1-1 system with a single common voltage. And this may be key. Why? Now imagine that we have some large array, shared control. Then you can imagine that one gate holds just one potential, and that potential then loads a single electron in each quantum dot underneath the shared control. It may also be useful even if one is not pursuing shared control. For example, for dedicated electronics that has some few output voltages, and the system needs to work with those voltages. So it seems that this is now possible today. How can we do this? Better materials? Well, we see that heterostructures offer more knobs. And I want to focus on that. So here you see an example of silicon. In germanium, it's rather the same. Both are heterostructures. There is a silicon or a germanium quantum well, where we define our quantum dots in. And then there's this interface between the dielectrics and the silicon germanium layers. Nowadays, there are traps inside this layer. But making use of our electrical voltages, we can tune the position of those traps. This has often been regarded as a bug. For example, it leads to hysteresis. And so people would worry that each time that we cool down a device, it's slightly different. But actually, it turns out to be very reproducible. So here you see this kind of hysteresis diagram upon 2 different cooldowns, where in addition to that, we apply what we call stress voltages. So we apply a large, either negative or positive voltage pulse. And after this voltage pulse, we directly measure, in this case, the turn on or pinch off of the device. And you see that we can tune the pinch off and the turn on voltage of these devices by applying these stress voltages. Great. Now let's see what happens if we're going to do this at the single electron level. For example, here I showed you that we can navigate to this 1-1 state at 1 volt. We make use of these stressing gate voltages to do that. And to kind of demonstrate the powerfulness of this approach, we can define a sequence where, for example, here we have the 1-1 state at 1.1 volt, applying these stress voltages. And in the lower right, you see the evolution of the gate voltage after applying these stress voltages. We can do this further, for example, to navigate to have the turn on at 1.2 volt, back to 1 volt, and back to 1 volt again. Right? So now, by making use of this additional interface, we have a knob to control the uniformity. So even if the materials are not perfect, even if the fabrication is not perfect, then still electrically we can tune and navigate the system to make it uniform. And this may have quite some consequences in the control of larger systems. Now one may argue, okay, this is great, you're making use of the traps. But if devices get better, if materials get better, maybe at some moment we don't have traps, because in the end we don't want to have noise, so these should go away. Then maybe there's a time where we'll see that heterostructures are going to be used, that we have additional layers to navigate and, for example, tune the lever arm in one quantum well by controlling another quantum well. This also connects to another possibility. Heterostructures we're now exploring mainly a single quantum well. But there's nothing that holds us from growing multiple quantum wells in the same system. For example, here you see a double quantum cell system in germanium. So it's a silicon germanium layer, germanium quantum well, silicon germanium layer, germanium quantum well, and another silicon germanium quantum well on top with gates to control it. This is a double quantum well, and there's quite some opportunities in this platform. One may imagine, for example, to have qubits in one plane, sensors in the other plane, maybe quantum links in the other plane to control qubits that are more remote from each other. That, of course, is very appealing from a scaling point of view for quantum computation. One may also imagine to have novel types of qubits. For example, a qubit that's located over these two interfaces, a certain flip-flop type of qubit, for example, where the different quantum wells are optimized to optimize for such a vertical qubit. Quantum simulation may also be very appealing in this platform. For example, one may explore excitonic interaction between two quantum wells. If one can make 3 quantum wells, then maybe the middle quantum well can act as a repulsive layer to create an interactive interaction between the outer layers. Imagine a hole coming into the top layer, pushing away a hole in the middle layer, and thereby attracting a hole in the bottom layer. Then effectively, there's an attractive force between the outer two layers. This may be regarded as a boson, and so maybe in these multi-quantum well systems, there's a possibility to create artificial superconductors in these systems. So multi-quantum well systems may be explored for quantum computation, quantum simulation, and building of novel types of qubits. A key ingredient, of course, is can we also control these quantum wells? And what it turns out is that quantum dots in these different quantum wells have a different size. And as a result, they also have a different relative lever arm in the coupling to the different gates. And this allows us to individually control these different quantum wells. And so here, for example, you see a stability diagram where we can independently load a hole in either the top or the bottom quantum well. And we can even see the transitions between the two because nearby charge sensors have a different sensitivity to these two quantum wells. This is very basic research science. We don't know how good qubits will be. We don't know how far we can go, but I think it shows the richness of the semiconductor toolbox. And exploring these will also outline a strategy towards scaling to larger systems. As we've seen with generations going from silicon to germanium and strained silicon, in all these developments, there was also directly an ability to control larger devices. Exploring the richness of these heterostructures may also enable the next generations of quantum devices.